Hello everyone, it's me again. It's that time of the week where I have another video for you so that you're ready for the experiment. The experiment is going to be, again, pretty straightforward, but we have to find out about some more components and how to place them. But the experiment should be fun because we're going to be using a new component. Actually, we're going to be using a couple new components that I'll describe shortly. So let's just start maybe with the description of the new things, the new components. So first of all, we're going to be using this thing called the integrated circuit. So basically it's like a chip, and it has the circuit inside that built in silicon. So this contains many components, but for us, we don't really care what the components are inside. We just worry about how to utilize it, how to use it as a functional block. So that's very important. So you can design without knowing exactly what's inside, as long as you understand some basic things. So this device is called a timer. A timer. So it's used to generate typically rectangular waveforms of all kinds at certain frequencies, certain time durations, etc. But basically, this device is, you can call it even a clock because it generates these time signals, timing signals. Regardless, let's just talk about some of the physical characteristics. So this device is usually denoted as a LM555. Sometimes it's maybe denoted as NE555. Refers to the same device. You may even have some extra letters after the 555. That's fine. So the device that you have in your kit, it may say LM555CN as it's shown on the picture here. It might be a little bit different, but they all work pretty much the same. So these devices are in what's called a DIP8 package or dual inline package. So you got two rows of pins. So this has 8 pins. And it turns out that the pin-to-pin distance is about 0.1 inches. It'll fit right into the our breadboard as we know it. So the only thing you need to know about this is how to denote the pins. So when you look at the integrated circuit, you will notice this round notch or like a little circle that's embossed in. That denotes pin 1. So this pin right here is pin number 1. Sometimes in other circuits, you might have a little notch on top here. So when you look at the integrated circuit from the top, if you see a notch, you will start counting from the left column or the left row, as the case may be. So in this case, this notch means that this is pin number 1, and then pin number 2, 3, 4, and then you continue on the other side, 5, 6, 7, 8. So this would be like 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's all there is to it. And again, the views are normally given from the top. So sometimes you will have these schematic diagrams seen from the top. So I give some of the details over here. But you know, when you see the integrated circuit as views from the top, if you see a notch on top of the circle, you just start counting 1, 2, 3, 4, 5, 6, 7, 8. Just counterclockwise counting. And in the 555, the pins have these names. And in some documents, these may be abbreviated. I give you the abbreviations down here. So we have actually a model in our simulator for this block. And in the simulator, these are abbreviated. And the simulator, it might say NE555. Again, don't be alarmed that it's not the same exact naming for it. Okay, so this is the first building block that we will use. And like I said, this will fit right into the breadboard. I will show you how to do that in a second. Okay, so the next building block you will see when we do our circuits is the capacitor. Now, we've already seen this capacitor in the lab, already from the last lab, experiment number 5. It was a 0.1 microfarad capacitor. This capacitor, we will use again in experiment number 6. This capacitor is not polarized. Now, what was polarized means? It means that there is no plus minus terminals on this. Just like a resistor. Resistor is not polarized. You can put it one way or the other way. It doesn't matter which terminals you choose when you build it. Okay. Now that's not true for all of the electronic components. So again, this 0.1 microfarad capacitor is not polarized. It's a ceramic capacitor. You can put it any which way you like. Now, there's something called the electrolytic capacitor, or in particular aluminum electrolytic capacitor. These devices are polarized. And in your kit, you have 3 of these. You have one 100 microfarad capacitor and two 220 microfarad capacitors, and they look like these little cans, okay, these little cans, and there's 2 terminals coming out. And in this case, the plus and the minus does matter, so you have to be very careful. And you'll notice that on these cans, one side has these negative signs. That's a little strip pointing to where the negative terminal is, negative lead is. Okay, so you can very easily see that this terminal is the negative and this terminal is the positive. And if the schematic diagram says put the positive here, put the negative there, you do that. Okay, so don't do it just randomly. Make sure you put the minus and the plus where they're supposed to be. Also, you notice that the minus terminal is shorter. Okay, so the minus terminals is always shorter. It might not seem exactly in some of the diagrams, but if you look closely at the kit, and if you examine the components in your kit, you will definitely see that the negative terminal is shorter. Okay, so this is the 100 microfarad, and this is the 220 microfarad. Again, you can see very clearly the negative side is shorter, and the negative side is shorter. Take a look at that, and once you see it, once you know what you're looking at, it's very clear. Okay, so these are the 2 capacitors that are polarized in your kit. In this experiment, we will be using the 100 microfarad capacitor. Okay, 100 microfarad capacitor. Okay, the next thing we'll use is a light emitting diode. These are like little lamps. Okay, these are also polarized. These have a plus and a minus sign. On the schematic diagrams, also in the simulation, you might see this arrow looking symbol with a flat side, okay, like this, with a vertical line. So the arrow points to the negative side. So the positive is on this side and negative is on that side. Positive is called an anode, the negative is called a cathode. And on the actual physical component, if you look at it from the top, okay, from the top like this, you will see one side is flat. One side is flat where the other side is circular. The flat side refers to the negative side. So here, this left is the positive, and the flat side is the negative, as shown over here. And you'll see that because it's a lamp, you'll see these little 2 arrows or some kind of arrow, circular, some kind of wiggly lines coming out of it. It just means that it's a lamp. Okay. Also, just like the capacitor, you'll notice that the negative terminal is actually shorter. So the negative terminal is definitely shorter on these LEDs as well, as denoted on all these diagrams. I put enough pictures here to just give more information, but once you see it, it's pretty clear what's going on. Negative is the shorter lead, flat side is the shorter lead, and once you see that, once you know what you're looking at, there's not too many things you really need to know. Okay. All right. So these are the new components that we'll have, and the way you will enter them or put them into the breadboard is really up to you, but I just wanted to give you at least one indication about how to put the integrated circuit, the LM555, right? So the LM555, it has 8 pins, and typically when you put it into the schematic, you will put it in a way that the 2 rows, or the 2 columns, as the case may be, will be parallel to the little valley that's in the protoboard, the breadboard. So let me show you that. Okay, so here's a picture of the protoboard. Okay, and so this is one of 2 or 3 that's typically on the breadboard, but here's the little valley, right, that runs through. And remember that when you look at any one of these columns of 5, those are connected together. So typically what you do is, or what you should do, is when you take your integrated circuit, you could simply just move it in one of these locations. Just be careful, line up the holes, and gently with your thumb press on top. Okay, press on top to push the integrated circuit, in this case the 555, into the breadboard. And now, once you've done this, any one of these columns, right? Any one of these columns will be, for example, pin 8, right? If you notice carefully, here's the notch, here's a circle. So this, right? This whole column right here, This whole column right here is pin 1. This whole column is pin 2, pin 3, pin 4, right? And then so on and so forth. Pin 5, pin 6, pin 7, pin 8. So that's the way you should do it. Just as a suggestion. On top of that, what I would also suggest is that you run your power supplies on these top lines. If you remember, all these top lines are really connected together, right? So this top line here, top row, is connected together. And if you look at the integrated circuit itself, right? If you look at the integrated circuit again, pin 1 is ground and pin 8 is power supply. So that's actually perfect to route this. So what you can do is something like that. And these are just suggestions, right? Just suggestions. What you can do is you can run a wire from this terminal all the way to your power supply positive terminal. Similarly, you can run a wire from here. Okay. Again, when I press on this, you see that all those yellow are connected together basically. So I can run a wire from here out here to my negative terminal. Again, this top is all the same. So if I go up here, right, that terminal is basically all the same. All these are the same. Okay. And I'll route it again just to show you. Okay. So if I take this line, okay, the top nodes are all the same. So if I make the top, for example, my power supply positive, and I make this bottom my power supply negative, then remember, pin 1 has to go to ground. So all I have to do is put a wire from here to here, and I basically got it right now. This is connected to, pin 1 is connected to the negative side. And here, if I work a wire from here to up here, for example, that will make the pin 8 terminal, the positive terminal. I just wired up my 555 power supply and the ground terminal. Now, there's more to it that goes around it, including the LED, for example. You can bring the LED and place it somewhere here, and you notice that in this LED, there's this terminal that's the plus or the minus. You have to make sure you know what you're talking about, right? You can always go back and check. You can always go back and check to see, okay, where was my plus terminal, where was my minus terminal? Well, if you notice here, this curved lead is always the long lead. That's the plus terminal. So in other words, here, this is the plus terminal. Now, how you connect it up over here, that's up to you. Same thing with the capacitor, right? Here's the capacitor, okay? There's the plus side and the minus side, and if you look closely, right, if you look closely, the band that has the minuses is on this side. So how you connect these up with the rest of the circuit, and there's more components, I just leave that up to you. But I'm just giving you a suggestion that to start it up, that this is how you locate the place to 555, and this is how you wire the positive and the negative sides of the power supply that it needs to be hooked up to, because this integrated circuit needs power to operate. In this particular case for experiment 5, we're going to be just using 5 volts that you set from the power supply. Okay? Does that make sense? When you see the diagram, I think it'll be clear. Also, I should let you know that to remove this integrated circuit, don't try to just yank it out. The best way to do it is actually to take your pen or pencil and the pointy end, just put it right under here, under the integrated circuit, and just put it under the integrated circuit itself in this valley. And as you rotate it up and down a little bit, you will see that the integrated circuit will come out pretty easily. So just use it to kind of rotate it up, or just kind of notch it up a little bit, and you'll see that it will come out very nicely. Don't yank it out, because if you do that, you'll damage the integrated circuit, and or the pin may break into one of the holes that you just put it on, and that may damage the board. Okay? So I think with this, you should have a good idea about the components and roughly how to start placing them, okay? How to place them. All right, so now let me show you the simulations. Okay, so I'm going to give you these things. So here's the first circuit that you will build, okay? For example, here's the 100 microfarad capacitor, electrolytic capacitor. Notice the positive side here, okay? Here's the power supply. Notice the pin number 8 is going to the power supply. Notice that pin number 1 is going to ground, and so is this, right? So this side of the power supply, it's going to ground. So these triangles are ground symbols, and they are all connected together to wherever your ground terminal is. In this case, those would all be connected eventually, right? They will all be connected to this terminal down here. Somehow when you wire everything up, those ground symbols, those triangles, should end up somewhere down here because all these are the same terminal. It's the negative side of the power supply, okay? So as you can see, this is the model for the 555, and it's actually all ready to go. And this is what I want you to wire up as well. So what you will first do is you will take the circuit, run the simulation. Okay, so you run the simulation. I'll just run it for you to show you. Okay, I'll close the other ones. And then after you have run the simulation, okay, you'll go and look at two terminals. One terminal is called a threshold terminal. So this is the terminal that controls the oscillations in the circuit, basically how the clock operates to generate the waveform. So if I basically, after I run the simulation, if I go to the schematic diagram with the schematic diagram highlighted, if I go on it with the my cursor, it turns into a red probe. I click on it, and here's the waveform. That's the first one I want you to look at. The next thing is called the output waveform, and the output waveform is shown right here. So if I click on that, here you see the so-called output waveform. Okay. Now the other thing is that here the two waveforms are on the same plot pane. If you want them to be on separate graphs, there's a very easy way to do that. And what you do is, okay, so you go basically on the graph window like this. You right click, okay, you right click, and then you say Add Plot Pane. So if you click on that, a new graph window shows up. And what you can simply do is you can simply take your cursor, go on the waveform, for example, V threshold, okay, so it turns into a little finger, press the left mouse button down and drag, and let go, and there it is, okay? So you can simply do this very easily. If you want to change the colors, for example, let's say you don't want the color of this V out, you just go with your cursor, right click, and then you can say, okay, I want my color to be green, okay? You can say, okay. I mean, it's up to you. So you can do things like that, but simply opening a pane, opening a new pane with a right click, okay, right click, add plot pane, and simply select the name from the waveform label and left click, keep the left click down, drag and let go, and then you can see the waveform like this. So from here you could see both of the waveforms, the so-called threshold waveform and the output waveform. So this output waveform is the voltage over here that we're applying to the circuit here with the 330 ohm resistor and the LED, and you should be able to see the LED blink. So it should blink, and this tells you when it blinks. So whenever the voltage V out is at the high level, 5 volts, it turns on, and then when it's 0, it turns off, on, off, etc. Okay, and you can see the duration it's on. So it's on for maybe about a minute. I'm sorry, 1.5 seconds on, 1.5 seconds off, roughly. But you can measure those things here. Okay, you can measure them. How do we measure things? Well, I'll show you that too. Okay, so let's kind of make this window maximized. Okay, so how do you measure something? Like for example, I want to know the distance between these pulses. Okay, so I want to know the distance from here all the way over here. Okay, in other words, I want to know the period of this pulse. What you can do is, if you left click on the mouse button here, the label with your mouse, you will see a little window that comes up, okay, and then it has these so-called cursors, right? So as you move the cursor, as you move the mouse, you see it says 1, okay, so that's the first cursor, and as you move it around, it tells you where the actual time and the voltage values are, right? So like right now, I'm at 3.32 seconds, 4.94 volts. As I move this way, 4.78 seconds, 29.99 microvolts, almost 0, right? So you can use this to go back and forth and measure the actual voltages and the time levels, okay? Both the time and the voltage can be measured with this. That's one way of doing just one signal. Now, how about if you want to measure the difference? There, what you can do is, if you go on the label again with your cursor, right click, okay, and then you say attach cursor, you can say first and second. So you can attach actually both cursors here and you can get a difference. So let's do both, okay? So first and second, we okay it. Now we have two cursors. They're both actually located on top of each other. And here's our cursor's kind of position. And you can see what this can do is it can do cursor 2 minus cursor 1. So what you can do is just grab cursor 1 and maybe you put it somewhere here, okay? And then you grab cursor 2. Again, I'm just moving the mouse button, okay? The cursor, the mouse location. And here's 2, right? So this does 2 minus 1, right? And you notice that it has a negative. That's because cursor 2 is at like 2 point something seconds and the cursor 1 is at 5 point something seconds. So if you want to have a positive number, right, you can just switch those around and you know, and put them here and here, and you know, you can just play with it until you see what you want, basically, okay? Like that. So apparently the difference is about 3.2 seconds, okay? You know, how much is this pulse on for? Well, then you can move the cursor to somewhere over here. You can tell, okay, that pulse difference here is about 2.44 seconds. The pulse width from here to here, from pulse 1 to cursor 1 to cursor 2. As you move your mouse cursor, right, over these two named cursors, 2 and 1, you can see them turn into a 1 or a 2, the number 1 or 2, and so you can locate where they are. You're going to play around with it a little bit, but you can get a pretty good sense of what's going on. By the way, you can also just take your mouse cursor, right, and the cross, if you just move it over and just leave it right there, you can see on the lower left-hand side, it says x equals 2.43 seconds, y equals something, right? So I can tell right away from there that the x position is 2.43, and this position is, for example, x is equal to 4.12 seconds. This position is 5.65 seconds. So just by looking at those values, I can determine the distance from here to here. I can just do the difference, right? I can just subtract, and I can do distance from here to here. So there's several ways of doing this. I'm just showing it to you so that you know how that's done. Okay, so this is circuit number 1. There's just one LED, and if you run the simulation, this is what will happen, and then you will build it. You'll build this. Building this will take a little bit of time. You're going to have to put the integrated circuit on there. You're going to have to put 2 resistors, right? All these resistors and components are in your kit. This is the 0.1 microfarad you used from last time. This is the electrolytic. So all these are in your kit, okay, including the 555 integrated circuit, okay? So this first circuit will take some time to build, but the subsequent circuits will be very, very easy. So if it's taking a little longer on the first circuit, don't worry, because that's perfectly fine, okay? So let's look at circuit number 2. Very similar, very similar. All we have done is we have added another R and an LED on top here to this output terminal. So if you compare these two, you will see that all we have done is we just added another R and an LED, basically, from here to the power, okay? That's all that is. So it's actually just 2 more components. Everything else, okay, everything else, if you look, okay, is exactly the same. Exactly the same, okay? So you put this together and, again, rerun the simulation and look at the waveform again. In fact, the waveform should be the same, but hopefully what you should notice is that these LEDs are blinking alternately. This one on, this one off, this one on, this one off, and so on and so forth. And again, run the simulation and then simply probe these waveforms. You know, the threshold and the out. You know, and then you can even add a plot pane if you want to. But I might actually give you a file which does it automatically. So if you run the simulation, if you hit the running man and you automatically get the waveforms like this, you're kind of done. There's nothing for you to do, like add a pane or something. Okay? So hopefully there'll be less pain for you. Sorry, I have to just say that. All right. Anyway, so that's circuit number 2. Circuit number 3 is this, okay, which looks very similar to the first circuit, except that notice that the capacitor down here is now 0.1 microfarad. Okay. Now, in this particular circuit, okay, this circuit is actually not ready yet because what I ask in the third part of the experiment is that I want you, okay, to pick the values of RA and RB. C has been already picked. This has already been picked, okay? But I want you to pick values of RA and RB such that this output waveform has a certain shape, okay? So if you just run the simulation, it'll run, okay? And then you can even look at the output, okay? You should look at the output, okay? It looks like this. And you know, maybe you can run it a little longer, a little less, but anyway, this waveform is not going to be what I want, okay? In fact, we can run it maybe a little longer, okay? Maybe run it for maybe 10 milliseconds, okay? So you can see it a little better maybe how it's going on. But you're going to run the simulation, and you know, it's going to give you this, but this is not what I want. It'll be spelled out as to what I actually want, what I want the waveform to be, how long it should, what should be the period, how long should be the time where it's 5 volts, how long should be the time it's 0 volts, etc. So what you need to do is you need to pick values of RA and RB so that you do get what I want. And there's some expressions, there's some formulas for allow you to do that, but you do have to play around a little bit, and you do have to try to use the components that are in your kit. So it's going to be a little bit of a challenge, but you can see if that's going to work or not by saying, for example, okay, I want to put for RA, you know, 3.3K. That's in my kit. So put the 3.3K here, run the simulation, and see if you actually do get what you're looking for. And when you're done, report the values of RA and RB, and of course, report the waveform that you get. Okay, make sense? So that's basically it. It's a little bit on the long side in terms of the initial circuit, but I don't think it's gonna be that bad because the second and third ones are very, very easy. You just keep the same circuit structure, and I think it should be going smoothly from that point on. And like I said, I'm going to provide you with the circuit files, the simulation files, to pretty much do the simulations so that you can verify what you're seeing on the schematic, on your constructed breadboard, you know, the actual hardware. So I hope this helps you, and I hope that you know, you have fun with the flasher circuits, and then you understand how integrated circuit can be used to generate waveforms. And of course, we're just touching the tip of the iceberg. So much more can be done with this integrated circuit, but this is the very, very basic that you need to understand to go forward and understand the other more complicated circuits that you might encounter. So thanks very much for your attention, and I will see you in class tomorrow, and good night for now. See you next week.